A microwave filter is a two-port network used to control the frequency response at a certain point in a microwave system by providing transmission at frequencies within the passband of the filter and attenuation in the stop band of the filter. They represent a class of electronic filter designed to operate on signals in the megahertz to gigahertz frequency ranges. This frequency range is the range used by most broadcast radios, televisions, wireless communications, and thus most microwave devices will include some kind of filtering on the signals transmitted or received. Applications can be found in virtually any type of microwave communications, radars, or test and measurement systems. There are four different types of filters. The first one is a bandpass filter, which selects only a desired band of frequencies. Second one is a band stop filter, which eliminates an undesired band of frequency. The third one is the low pass filter, which allows only frequencies below a cutoff frequency to pass. The fourth and the final one is the high pass filter, which allows only frequencies above a cutoff frequency to pass. For this project, we chose a bandstop filter. In signal processing, a bandstop filter, also known as a band rejection filter, is a filter that passes most frequencies unaltered but attenuates those in specific range to very low levels. Bandstop filters can be made by placing a low-pass filter in parallel with a high-pass filter. For this project, we found a paper on a compact microstrip bandstop filter. The authors of the paper are S. Falasade and M. Tayarani, and they are from the Department of Electrical Engineering, Iran University of Science and Technology, Iran.
The bandstop filter is a type of frequency-selective circuit which passes off frequencies with the exception of those within a specified stop band, which are greatly attenuated. It is an important component in microwave and millimeter wave applications to reject higher harmonics and spurious passbands. With the recent advances in microwave integrated circuits, there is a great demand for compact filters. In this paper, a new design of a compact bandstop filter using defective microstrip structure by etching open square ring is proposed, and its resonant frequency is extracted analytically by using lossless transmission line model. Figure 1 illustrates the configuration of complementary open square ring DMS in the center of the microstrip line. Figure 2 is the full wave simulated S parameters. We will be talking about them in the next few pages. Here is the implementation of our filter. The dimensions and substrate informations are listed here. We use the same substrate for all simulations. The device also provides the band rejection property of 30 dB at the frequency of 7 GHz.
In order to analyze this resonator, there is a model called microstrip coupled lines, introduced by the paper. As you can see here, this is the coupled line model for our resonator. This model can simulate the resonator's behavior under different frequency. Here is a graph of the results. The solid line is the coupled model's response output, and the dotted line is the actual output of the resonator. As you can see, they almost match each other. However, there is a simpler model to represent this resonator. The coupling effect in the transmission line model has ignored because of a very narrow physical width of the microstrip coupled lines. So, we can simply move the small middle section part to L2 and make them have the same length just like this figure. After doing that, we can get the formula like this. In this formula, Z0 is just the impedance of the port, and A, B, C, D are 4 parameters. The detail of how to calculate these parameters are listed in the next slide. Here, the default Z0 is 50. Theta can be calculated by beta times L. Z1 and Z2 are the impedance of lines with W equal to omega 1 and W equal to omega 2 respectively. When the absolute value of S21 is 0, the filter creates a transmission 0.
Since we couldn't build a micro-notch filter physically, we're going to use OpenEMS, which is a program based on MATLAB to simulate the micro-notch filters. In this link, there's a tutorial on OpenEMS website that we're going to use to setting up the micro-notch filters. There's a few parameters that we need to keep an eye on before we setting up the simulation, which is the size of the filter, substrate parameters, dielectric constant, and the materials of the filter. We're expecting to get the same output as the one mentioned in the paper after we put the model into OpenEMS, which is the one that is showing you in the graph.
So in conclusion, a bandstop filter works to screen out frequencies that are within a certain range, giving easy passage only to frequencies outside of that range. The paper that we used for this project proposed a new compact and high rejection level bandstop filter by using a defected microstrip structure. The transmission line model is introduced for this resonator and the corresponding resonant frequencies extracted analytically. This new compact microstrip bandstop filter can be very attractive for the applications of MMIC design.